Hello, everybody, and welcome to today's webinar, Harnessing Artificial Intelligence to Improve Glaucoma Management with Dr. Linda Zangwill. My name is Elena Sturman. I am the President and CEO of the Glaucoma Foundation. Since our founding in 1984, the foundation has worked to encourage and support basic and applied research in glaucoma with the goal of preserving and restoring vision. We have provided millions of dollars in seed money for innovative projects, and we continue to support a space for scientists to think creatively and gather the data they need to pursue major grants from entities such as NEI and NIH. Above all, TGF is dedicated to improving the lives of people with glaucoma. Because there is currently no way for your doctor to predict how your glaucoma will develop over time, the Glaucoma Foundation issued a challenge to scientists last year. Could they create an algorithm capable of analyzing optical images to forecast the progression of your disease? If so, your doctor would have access to important new information to guide them when making decisions about your treatment, particularly if and at what stage you would benefit from surgery. Dr. Linda Zangwill of University of California, San Diego, proposed to us that she and her team can, in fact, devise this algorithm, and the foundation has awarded them our largest ever grant to work on the problem over a 2-year period. Dr. Zangwill is a PhD and a professor of ophthalmology in UC San Diego, where she serves as the Director of Clinical Research of the Hamilton Glaucoma Center and Director of Imaging Data and Evaluation and Analysis Reading Center. She has published more than 350 manuscripts in peer-reviewed journals. She is an elective executive committee member of the Glaucoma Research Society and an Association of Research in Vision and Ophthalmology Gold Fellow. Dr. Zangwill has continuously been funded by National Eye Institute for 25 years as principal investigator for the diagnostic innovations in glaucoma study and, more recently, the African Descent and Glaucoma Evaluation Study. Her clinical research focuses on improving our understanding of the complex relationship between structural and functional change over time in the aging and glaucoma eye, developing computational and machine learning techniques to improve glaucoma detection, and identifying risk factors that can predict rapidly progressing glaucoma. Today, Dr. Zangwill is joining us to talk about artificial intelligence in ophthalmology and give us an overview of latest development in the use of AI to automate and improve the management of glaucoma. I would like to thank Santen for sponsoring today's webinar. Santen is a global leader in ophthalmological research and development, the production and marketing of related pharmaceuticals and medical devices. We are incredibly grateful for their partnerships and ongoing support of TGF's educational programming. If you have a question to Dr. Zangwill, just type it in using the chat or Q&A button on your screen, and we will do our best to answer it during our Q&A session at the end of the talk. And now, ladies and gentlemen, please welcome Dr. Linda Zangwill.
I want to thank the Glaucoma Foundation for inviting me to give this talk today on harnessing artificial intelligence to improve glaucoma management, challenges and opportunities. I want to acknowledge my financial disclosures and thank again the Glaucoma Foundation for supporting us. As everyone here knows, primary open-angle glaucoma is a major health problem, a leading cause of blindness, and over 130,000 individuals are legally blind from the disease in the US alone. The number of people with glaucoma will increase worldwide to almost 112 million by 2040. And glaucoma is asymptomatic in its early stages. Here we can see how glaucoma affects vision. Normal vision on the left, and glaucoma, loss of peripheral vision, primarily in the early stages on the right. And that's why it's asymptomatic. Your body is pretty smart. And your eyes will look a little to the right or to the left, so you won't even notice that you're losing this peripheral vision. So how does this work, or what happens in glaucoma? Well, glaucoma is a disease associated with progressive loss in retinal tissue and visual field damage. Here is the optic nerve head, part of the back of the retina. And as you're seeing something, the imprint of that image goes into the retina and through the optic nerve to the brain, where you see things and recognize objects. This part here is what the clinician will look at when they're examining you for glaucoma. And when they're figuring out whether your visual function is affected, you will have a visual field test, which many of you are very familiar with. And the black areas are areas where there is already some glaucomatous damage. So we have the visual field printout. And what happens is you have a normal visual field, and as you progress with glaucoma, hopefully you won't, it'll be treated well, you can have severe damage from glaucoma. And there's a number that is reflected in this that the clinician can use. And I'm going to come back to that when I'm talking about AI and predicting some of the features of glaucoma. So when you have a normal visual field, your mean deviation is close to 0, but as you get worse, it gets more negative. So more negative is a worse glaucoma, and I'll come back to that later in my talk. So here I can show you what the clinician looks like and how AI might be able to mimic what the clinician is doing. Here we have a normal optic nerve, normal tissue, but as you advance with glaucoma, this donut here is thinning. You're losing this neural tissue in your eye. And you're losing retinal ganglion cells and retinal nerve fibers and axons. And as you get more severe, you see less neural tissue here. And how does a clinician look at it? Well, they can have photographs. Photographs are qualitative. So the clinician will look at this and say, well, this looks fairly normal, and the visual field looks normal. Here I see a little bit of loss of neural tissue, loss of the neuroretinal rim, and there's some glaucoma damage here. Here is an eye with more severe damage, and the clinician will see that on the photograph. So I spoke about how we diagnose and monitor glaucoma with eye exams and photographs and visual fields. And I want to talk about optical coherence tomography, or OCT, which in contrast to photos, which is qualitative and subjective, the OCT provides objective and quantitative information. And it is pretty amazing. It's a 3D histology, really, virtual histology of the retina. You can see this cube, and this is what the image looks like. And an OCT is analogous to ultrasound, but instead of using sound to identify objects, it uses light to differentiate between different layers of the retina. Here's a schematic of the different layers of the retina, and here's an OCT that's color-coded. So it really shows everyone, the clinician, the different layers of the retina. However, the glaucoma treating clinician usually just sees an OCT printout, which does not use all the information that is available in the OCT. And I think AI can exploit the information in the OCT to help the clinician better manage glaucoma. So I want to show you a printout of an optic disc or optic nerve head scan from the OCT, the healthy eye and a glaucoma eye. Here are all the different layers. And this is the layer that this particular scan is looking at. It's called the retinal nerve fiber layer. And as you see here, the thicker nerve fiber layer, which is healthy, is red or yellow here. And the glaucoma eye, that's missing that red and yellow, meaning there's thinning of the nerve fiber layer and you're losing neural tissue, which is affecting your vision. The OCTs generally also provide a deviation map to the clinician, which shows the thinning compared to normal. So in the glaucoma eye, this red area shows this is really thin compared to a normal eye. In the healthy eye, there's no red because it's a healthy eye and there's no thinning. We also can use the macula scans to evaluate glaucoma. And I just want to share that with you because it uses different layers, more of the layers, the ganglion cell layer and the inner plexiform layer, but the process is the same. The red and yellow are the thicker layers, and here there's deviation or thinning. Now, clinicians integrate this information from multiple sources, from the photograph, from the visual field, and they also look at patterns. And there's specific patterns that are anatomical and pathophysiologic to glaucoma. where the visual field in the upper area maps, or that's called the superior region, maps to the optic nerve head on the the superior region maps to the inferior region or lower region. So if you have damage or loss of neural tissue here, you're going to see it in the visual field. So this is what happened here. You see there's some damage or some black here, the visual field, and you can see it matches this loss here that the clinician sees. And AI can really help the clinician integrate this information. So what is AI? I've been mentioning that quite a lot. AI are programs with the ability to learn and reason like humans. And machine learning is and I'll be using these terms kind of interchangeably, artificial intelligence, machine learning, and deep learning. But machine learning are algorithms with the ability to learn without being explicitly programmed, where deep learning does that, but with lots and lots of data. So beforehand, without machine learning, you would have to really tell the computer exactly how the relationship is, a specific formula or an algorithm. With machine learning, the machine learns by itself the relationship. And that has been a tremendous breakthrough. There's also something called big data and data science. So I'm going to show you what we can do with big data sets that are too large or complex to be handled with traditional data processing software. And data science is a science that deals with vast volumes of data using AI. And so all these are really quite important to make the AI breakthroughs that we're hoping to make. About 10 years ago, data scientist was considered the sexiest job of the 21st century, at least according to the Harvard Business Review. So as most everyone knows, AI is dramatically changing our lives. We have Amazon and Netflix. Every time you click, you get a recommendation to buy something else or to view something else. We have personal sensors and medical tests. Autonomous driving is a little bit bumpy road, but I think it's coming. And AI is transforming healthcare, and actually ophthalmology is leading the way. The FDA granted approval, its first AI device that it was granted approval for was for an ophthalmologic device that looked at photographs to detect diabetic retinopathy in primary care. Here, Google's AI doctor gets ready to work in India. India fights diabetic blindness with the help of AI. In addition, the eye is a window into the body. The vasculature and some of the features in the eye reflect diseases, systemic diseases in the body. Google hopes AI can predict heart disease by looking at the retina. And Google's work using just retinal photographs predicted age, gender, smoking status, etc. Alzheimer's, Parkinson's, other diseases, cardiovascular diseases, are looking at the retina because there's easy access to imaging. AI is so important that it's considered the fourth industrial revolution. So how does this work with the deep learning that I mentioned? Well, here's a simple neural network that's been around for 20, 30 years. A deep learning network has many different layers. And in this example, here's a photograph, and some of the layers may look at some of the borders, some may look at some of the features, an eye, an eyebrow, and see that this face is Sarah. Similarly, we can input into an AI algorithm photographs, visual fields, OCTs, and the output would be glaucoma, yes or no. We have to train it to do that. And there's two different main types of machine learning that have this training. Supervised learning, which is the kind that I just gave an example for, we have lots of labeled data. That these visual fields, for example, each one would be labeled glaucoma or not glaucoma, and the machine learning classifier learns from that labeled data. So when it's presented a new visual field, it'll say whether it's normal or glaucoma. So there's the input and the prediction. In unsupervised learning, you have lots of visual fields, but there's no labels. So what does the machine learning classifier do? It identifies patterns. And you can see here some visual field patterns that were identified with machine learning. And ophthalmology is really leading the way because we have large data sets with good quality ground truth and labels. Other medical specialties the patients don't get imaging as often as they do in ophthalmology. You can have an OCT a couple times a year, once a year, a visual field test, et cetera. In most other medical subspecialties, they don't have this kind of data that you can acquire in a second or two, and it's non-invasive. We also have electronic health records, public data sets, which I will share with you. Now, a colleague of mine, Michael Goldbaum, a retina specialist at UCSD, in 1994 did a machine learning research and concluded that a neural network, machine learning, can be taught to be as proficient as a trained reader in interpreting visual fields for glaucoma. That's quite a long time ago, almost 30 years. So what took so long? Well, now we have the computational power, the large data sets, the public data sets, and the software to make deep learning possible. You can see that there's been an exponential growth in the AI and glaucoma research publications. This is from PubMed. This is a government website that you can look at publications. And you can see just in the last few years, the tremendous amount of growth in AI publications. So what I want to talk about now is bringing the background in glaucoma and what I shared with you with AI to glaucoma management, glaucoma detection and clinical workflow. So there's three main ways that AI can help. It can automate glaucoma detection that can be used in your clinic, in your ophthalmology clinic. It can also be used in underserved areas, telehealth, primary care. We can provide clinical decision support with visual assistance to the clinician. Maybe you should look more closely at the optic nerve head in this particular region because AI is suggesting there's thinning there. We can also have predictive analytics or personalized medicine who predict who is the highest risk of progressing. We want to move from one size fits all to personalized glaucoma management. So let's say you have just recently been diagnosed with glaucoma. Maybe the clinician says you should come and have a visual field test every 6 months, an OCT test every 6 months. It's the same frequency. What we want to do is personalize that based on the information from your results to get the right test and the right frequency. And we think that machine learning AI can assist with this. At UCSD, our Glaucoma Clinical Research and Reading Center has an AI pipeline. So it's not enough to have all this data. If the visual fields are on the visual field machine, the OCTs on the OCT machine, you can't have an algorithm. You don't have it aware. You can program it together in a space that the algorithm can train and learn. You need to have it on a server in the cloud. And we're fortunate because we have had a reading center and large NIH funded studies, the Diagnostic Innovations in Glaucoma Study and the African Descent and Glaucoma Evaluation Study with colleagues in Alabama and Columbia, that we have a lot of data and we've been collating and building the infrastructure of this so that we can apply these AI models. So the infrastructure is really critical. Some colleagues say that 80 to 90% of AI research and development is data management. So we are set up for that. So I want to share with you some of our work. And as I mentioned, the AI and glaucoma research is just tremendous. And I can't really acknowledge all my close colleagues who are doing fantastic work. So I just want to share with you a little bit to give you a flavor of the AI research and how it may affect glaucoma management in the future. I'm going to start with electronic health records. So a colleague of mine, junior faculty, Sally Baxter, used electronic health records, or EHR, to predict who would need glaucoma surgery in the near future. So she looked at admissions, hospitalizations, social history, blood pressure, et cetera. She did not use visual fields, photographs, or OCT in this. And she found using just UCSD data, and it was not a large study, all right, 300 or something patients, that the existing data in the electronic health record had some predictive value in identifying glaucoma patients at risk of needing surgery, even without this eye-specific data. And she found that blood pressure metrics emerged as predictors of glaucoma progression. And so we thought that using EHR would be important as a starting point, and we'd like to add the eye-specific data as well. I want to share with you this example of a big data. Now, glaucoma surgery prediction improved when Dr. Baxter used larger, more diverse, all of us data set. Maybe some of you are participants in this. This is a nationwide prospective cohort study aiming to enroll 1 million people in the United States. I looked it up today, and it almost has 500,000 participants as of today. And they have surveys, they have electronic health data, physical measurements, wearable sensors. And what Dr. Baxter did was she tried to predict glaucoma surgeries with this larger data set. So how do we know whether the model is working? Well, there's something called the area under the receiver operating characteristic curve, and you won't need to know that name. We shorten it with ROC or AUC. So how this works is a perfect classifier has a value of 1.0. And if it's just randomly assigning glaucoma or not, it has 0.5. So the closer to 1 is a better algorithm. So what she found was just using the San Diego data, the ROC was about in this yellow, about 0.67. But when she used this all of us data set, it got much, much better. However, she still was not using the photographs and OCT. So I want to share with you some of our work that we use photographs and OCT to predict glaucoma, to predict the severity of glaucoma progression, and to predict the severity of glaucoma visual field damage. I want to acknowledge Mark Christopher, a junior faculty in our department. So what we used here was neurofiber layer thickness maps, which I shared with you earlier. Thicker means more red and more yellow from optic nerve head scans. And we use 3 deep learning models. I'm going to focus on the nerve fiber layer thickness. It's the same as this, but not in color. It's in black and white. And the nerve fiber layer en face image, which isn't measuring thickness, but is measuring texture. It's measuring features of the different layers of the retina. And this is something that the clinicians are not provided in the OCT printout. We had about 1,700 eyes, and we compared that to nerve fiber layer thickness without deep learning. And what we found here's the ROC curve. What we found was that this en face image did the best. And anything over 0.85, 0.8 is pretty good. We want to get closer to 1. And that did much better than without deep learning. It did better than nerve fiber layer thickness also. So there's something that perhaps AI can help us understand and provide to the clinician in the future that isn't presently provided in the OCT printouts. When we looked at moderate to severe glaucoma, the deep learning algorithms didn't help us. It was pretty much the same as without deep learning. So when you have very severe glaucoma, you really don't need some fancy algorithm. The clinician and simple algorithms can work. However, when you want to look at mild to moderate glaucoma, once again, this RNFL en face image, the retinal nerve fiber layer en face image, did the best. As I mentioned, there's a lot of studies with using OCT. And here's a meta-analysis or review article that summarized lots of the studies that are being used. And once again, this is this ROC curve, and it's very close to this corner. So in general, there's good glaucoma detection accuracy using OCT, and it compares favorably to human observers. What I want to do now is use OCT to predict not glaucoma, yes or no, but predict the severity of glaucoma damage of the visual field. So how do we evaluate that? Well, here's the actual visual field MD, and here's a predicted. This is perfect discrimination. Here's the actual is about -10. The predicted is -10. The error is 0. That is, and we use the mean absolute error to evaluate how well the model is doing. This does not happen in real life, right? This is perhaps a real world prediction. It's a bit scattered. And here's one eye where there was a large area. The actual MD was 0, which means pretty normal visual field, versus -10, which is fairly severe glaucoma. This one, the AI algorithm didn't do very well. And this is what it really looks like in one of our studies, where we used actually one of the macula scans as input, and we predicted the visual field, and the mean absolute error was about 2.6 dB, which is pretty good. I want to go back to the same scans we used previously. And here the mean absolute error, we want lower error, smaller mean absolute error. And once again, this en-face image had the lowest error. So how will this affect glaucoma management? Well, we think that accurately predicting the severity of visual field damage from OCT imaging can help clinicians more effectively tailor the frequency of visual field testing to the individual patient. Perhaps in the future, the clinician will say to the patient, we can skip visual field testing this visit, as predictions from OCT suggest that it's unlikely your visual fields have changed since your last visit. Wouldn't patients love that, to be able to skip a visual field because the OCT, which really takes seconds, is suggesting that your visual field hasn't changed? Alternatively, perhaps the OCT suggests that there is a change in the visual field. Maybe we should move up that visual field test. So we want to personalize the management of glaucoma. And we feel that AI can really help us do that. I want to share with you now some of our work using photographs. Now, photographs are not used as routinely as they used to be in clinical practice because the OCT provides so much more information and it's objective and quantitative. However, there's many millions of people in underserved areas without OCTs, and there's several different companies and researchers developing phone-based photographs of the retina, of the optic nerve head. So what we did was we predicted glaucoma in healthy. Here we had about 4,300 eyes in this particular study. And once again, Dr. Christopher led the way for this. And the area under the ROC curve was very good, 0.91. And the visual field MD was about -4, which is not that severe glaucoma. Once again, if you have severe glaucoma, any algorithm will do very well. And again, there's lots of other colleagues who are working on this, and there's good glaucoma detection accuracy using photographs. And photographs can also perhaps be used in telehealth more easily, in primary care settings where they will not have an OCT, but a primary care physician can get a photograph, and perhaps there'll be in the future algorithms that will detect not only glaucoma, but diabetic retinopathy, macular degeneration from a photograph. And they will say, this primary care physician will say, you know, your eyes look like you probably don't need to see an ophthalmologist right away. Where another person, well, wow, the AI algorithm suggesting you need to see an ophthalmologist right away. This would really help get people to the care at a timely manner. I mentioned unsupervised machine learning, and it finds glaucoma patterns without labels. Here's just some nerve fiber layer patterns, some visual field patterns, and we're thinking that this could help the clinician perhaps identify patterns that they're not as familiar with or weren't aware that they happen as frequently as they do. We can also use unsupervised deep learning, and this was an autoencoder type of machine learning algorithm, where it will identify regions of interest where the clinician should look to see whether there's progression or not. The green areas here are areas that the AI algorithm suggested might be changing. So the conclusion here is the detection and monitoring of glaucoma progression can be improved by considering eye-specific regions of likely progression using deep learning. So to train this model, but there's a lot of pairs, the baseline and a follow-up exam, a baseline and a follow-up exam. And so the algorithm learned to see when these changes were happening. Dr. Belgeet and Dr. Bowd helped with this project. Many colleagues are using this AI to predict future visual field loss. And here's another application that is quite interesting. It combines the photograph and OCT together, and it's trying to estimate the nerve fiber layer thickness on the photograph. So it's training, the machine learning is trained with pairs of photographs and nerve fiber layer thickness maps, so that the algorithm will learn how to map the thickness onto the photo, which we can't really see the thickness here. Here we see the thickness. And with the prediction here, you can see what the prediction was. Here's the OCT. These are the true thickness values. And here's what the AI algorithm predicted were the thickness values. And they're very similar to the actual OCT values. So perhaps we can monitor with photographs and estimate the nerve fiber layer thickness to see whether the nerve fiber layer thickness is thinning or is stable. There are several challenges to using AI that I want to mention. The first challenge is training data matters, and artificial intelligence can be biased. Michelle Obama, Serena Williams, and Oprah Winfrey were identified as male by commercial AI systems, and gender and skin type bias has been identified. And just last year, June 2020, Microsoft decided that it will not sell police its facial recognition technology, following similar moves by Amazon and IBM. Now, how does this relate to health? Well, we want to have diverse data sets. We want to be able to generalize what the AI algorithm we develop at UCSD to different populations around the world. So you need diverse data sets. We're fortunate we have the African Descent of Glaucoma Evaluation Study that has diversity there as along with UCSD. Another aspect of bias is that your data set and labels your training data set does not represent the intended task. And this is a kind of a classic example. Colleagues wanted to predict pneumonia complications, and they had several different hospitals to try to diversify to get not one population. And the model found that patients with pneumonia and asthma were at a lower risk of death than patients with pneumonia, but without asthma. Well, that doesn't make sense. How can someone with pneumonia and asthma be lower risk? Well, what that training said was that patients with asthma who presented with pneumonia were usually admitted directly to the ICU, to the intensive care unit, to prevent complications. So that led to patients with pneumonia and asthma having better outcomes. So the model learned correctly. It's just that wasn't the right data set to use for their intended purpose. Okay, so there's also historical data may be biased. There's a lot of information about this or on the popular press about criminal justice system, hiring, lending, etc. So what's the solution? A solution is to use diverse training sets and test on independent populations. There's numerous examples. Here's one with US, Hong Kong, Nepal, India. We traded data sets at UCSD with Japanese colleagues to see if our algorithms would work. And ours did well in the Japanese. The Japanese didn't do well initially on ours, but it was because they hadn't had early glaucoma in their training set. So that way we learned that the training sets really matter. Another challenge is opening the black box. What is that AI algorithm doing? And for clinicians to gain trust in the algorithm, we really want to be able to share what they're doing. And there's a couple solutions. There's explainable AI, and that's a whole area of AI research on its own. And there's several different ways of opening the black box. One way to do it is with these heat maps. And these red regions are showing the most significant regions used by the model to make its decision. And this was very reassuring to us because we know that the glaucoma affects the superior and inferior region first. And perhaps this can be used to provide clinical decision support and guidance for the clinicians when they're looking and treating glaucoma patients. I want to show you an example, another example, where we use the OCT to predict the visual field damage. And we predicted not only overall damage, but a damage in certain sectors. So remember that pattern. When the upper visual field is affected, the superior, it means that there's damage to the lower or inferior optic nerve head. And that's what this is showing, that when the algorithm was predicting superior visual field damage, it was looking at the inferior optic nerve head. Similarly, when the inferior visual field was damaged, the algorithm learned automatically the patterns that are the anatomic and pathophysiologic patterns. Another challenge is how to integrate AI predictions into clinical practice. Currently, ophthalmologists need to log into separate information systems to review the electronic health records, to look at the visual fields, to look at the imaging data. So where should we put these AI results so that the clinician can access them very quickly? How should they be presented? It can't be 5 or 10 clicks. It has to be 1 or 2 clicks. Otherwise, the clinician will not look at it. And it has to be presented in a way that's very easy to understand. So we had a pilot study. And once again, this is a whole area of AI research, user experience, how to present the results. And what we did was we presented these visual field predictions from OCT, and we tried to integrate the OCT, the visual field. This is IOP, intraocular pressure. And what we did was we had 18 clinicians see whether they trusted this, whether it adds useful information, whether this will decrease the frequency of visual field testing. So this is a whole other area of AI research that I think is really critical. You can have the best algorithm in the world, but if you can't place it and present it in a way that clinicians will use it, it's not very useful. I want to acknowledge, again, the Glaucoma Foundation grant. And the objective of this grant is to use AI to predict which glaucoma patients will need surgery. And my co-principal investigators are doctors Baxter and Christopher. So we are merging the electronic health record, the OCT scans, and the visual fields to predict the need for surgery. And I want to acknowledge my other co-investigators because we are leveraging existing data from diverse research and real-world clinical glaucoma populations for the development and testing of these deep learning models. Dr. Weinreb from UCSD, Dr. Fazio Gurkin from Alabama, and Dr. Liebman, who you all know from Columbia, are co-investigators in the study. We want to personalize assessment and testing. We want to appropriately tailor treatment approaches to the individual, determine the follow-up intervals for ongoing monitoring, and more effectively engage patients. And a generalizable AI model that can accurately predict the need for surgery can dramatically change glaucoma management. I'm going to share with you an example, not glaucoma. This is COVID pneumonia at UCSD. So a UCSD colleague developed an AI algorithm relatively quickly during COVID to see whether they can detect COVID pneumonia. So they had a cloud-based system. So the X-ray went up to the cloud, algorithm came back, and once again, these heat maps were used to see whether this was COVID pneumonia. I want to share this is a very complicated system in order to do that. And that's just with an X-ray. Glaucoma has visual fields, OCTs, et cetera. So developing a quick real-time system is quite a challenge. So I mentioned some of the challenges and concerns. Training data matters, opening the black box. How do we integrate it into clinical workflow? There are also regulatory issues, privacy and ethical issues, medical malpractice issue, reimbursement that I didn't even mention. Are you concerned about the increase in artificial intelligence? No, but I'm concerned about the decrease in real intelligence. But to summarize, there are tremendous opportunities for AI in glaucoma management. Detection of glaucoma and other eye diseases, I mentioned, underserved areas, telehealth, primary care involvement, clinical decision support. We can improve the consistency and accuracy of clinical decisions. We can integrate it with clinical tests and risk factors. We can personalize glaucoma management and testing. We can identify who is at greatest risk for visual field loss. And there can be new insights into glaucoma pathophysiology by using aspects of the OCT that aren't used currently. And we can integrate smart personal devices, home testing, sensors. Perhaps the future of glaucoma management, you'll have a remote visual field testing. There are many available, phone-based retinal images, a handheld OCT to determine whether you have glaucoma and whether your glaucoma is progressing. I want to thank my computational ophthalmology team. Without that, it really does take a village to do this work. And thank you.
Thank you so much, Linda, for this absolutely fascinating talk. And there are so many examples of machine learning and how it can enhance human capabilities. And there is certainly true in healthcare. And now we'll go into questions from our audience. They've been writing and they've been sending questions via chat buttons and Q&A. So let's start with the questions. So first question is, given your focus on OCT, do you think it would make a difference if a physician could do a visual field using an AI application?
Yes, I think the visual field is not as is a little bit more variable than the OCT, right? You can, as a patient, sometimes you're more tired, sometimes you're not, and so I think moving to OCT could be helpful. But the visual field is still important because that really tells the clinician exactly what you're seeing, and I think AI can be used in both for both types of purposes.
Great, thank you. Next question. If there is such a thing as an average glaucoma doctor, can an average glaucoma doctor immediately interpret and use your data and conclusions? Do they need any additional training?
Well, I think so we don't want to replace the clinician. That's another concern, but we want to help the clinician and to provide more consistent and accurate diagnosis. And so the algorithms need to be summarized in a way that's helpful. And that's something we're working on. So I showed you one example where we're trying to present the predictions for visual fields to the clinician, but perhaps using these heat maps. And what I didn't mention specifically is the AI algorithm usually comes up with a probability from 0 to 1. So if there's a probability of glaucoma of 75, 80 versus 0.2, that can be helpful for the clinician, or it could be helpful if that heat map is showing an area so the clinician could look more closely at that area, look at the visual field in the area that would be affecting, or look at the eye, look at the OCT. I think that answered the question, but if it didn't, please let me know.
Thank you. Next question is more general. Why did you become interested in AI, and how long ago did that happen?
Oh, so I've kind of run a computational ophthalmology team for many years, and I really felt that was before deep learning, and so our progress was slow. I was working with colleagues, and I would tend to recruit postdoctoral fellows in computer science, and that's been so we've built a team. And the last few years, because of deep learning taking off, and because we've been fortunate because we always had a reading center and a data coordinating center coordinating our data, we had that ready to go. And so I'm actually an epidemiologist by training, so I am not that technical. I don't program, I don't do any of that, but I hire fantastic people and I collaborate with fantastic people who can do the work. And I really felt this was an area that could really help. So the clinician can spend more time with the patient, figuring out how to treat them, discussing their disease, discussing treatment options, and less time doing the clinical analysis. And so that's what I'm hoping that this will move to soon.
Perfect. Thank you. Next question. Have you looked at, I just hear this. Have you looked at the prediction longitudinally? For example, can we predict later onset of visual field damage from OCT even when visual field damage is not concurrently there?
Yes, that's what we're trying to do, because often, obviously, you need some neural damage to cause the visual field to change, to have some damage. So the question is what you can detect first, right? So yes, we're starting to do that work, and others are starting to do that work as well, is predicting longitudinal. And that's what we want to do. We want to predict who will need glaucoma surgery 6 years, 6 months, 1 year, 2 years from now. Similarly, we want to be able to predict who will progress. And many colleagues are working on that and have published in that area. And we are also have some preliminary results in the area. And that's exactly where we want to go. So that was a great question.
That's great. Next question. Wow, questions are, yeah, I want to apologize in advance if we won't be able to answer all of them because questions are just popping up. Next question is there a way to access the end-phase image from various OCT platform providers at the practice level and add its analysis to the analytic dashboard?
Yes, and actually a colleague in Hong Kong developed it independently, a texture-based method. And how to commercialize this is another and how to bring it to market. And that's probably another challenge that I didn't really mention, but there's a lot of studies and background and material you have to present for an FDA or to bring it to commercialization. But some of the companies are interested in this. This particular one is further ahead than UCSD in terms of commercialization. It's called ROTA, and I from Dr. Chris Luong in Hong Kong. And so he's really moving a little bit faster than us in terms of bringing it and having some of the OCT instruments use that. So I think that's really the goal, obviously, is to not just have it as a research platform, but to have it incorporated into OCT instruments.
Mm-hmm. Thank you very much. Next question. Is AI beneficial for all types of glaucoma, open, closed angle, high normal pressure, etc.?
I think that each one has its own AI algorithms, and I should have mentioned that I was really focusing for my talk on primary open angle glaucoma. But closed angle glaucoma, there's a whole other set of diagnostic tests that are used, and that AI, I'm not working on that area, but colleagues are working on using those diagnostic tests for closed angle glaucoma, and whether it's a normal tension, not normal tension, et cetera. Those are all being used, and we're trying to figure out if the AI algorithms are generalizable to all those types, with people with elevated intraocular pressure, people without. And those are things that we need to look at when we're looking at not only severity of disease and how it affects different populations around the world by race or ethnicity, but also by types of glaucoma presentation. So that's these are all great questions.
Excellent, excellent. Next question. UC San Diego is working on AI models since 1994 with a lot of support and data. When is your perspective of an FDA approved model by UC San Diego? When is it coming?
Yes, and we do have some patent pending things, and that's just a whole nother set of experiments, set of regulations, regulatory hurdles to go through. So I don't have any predictions on that, and that it's I'll be frank, probably others might come to that quicker than us, who are already having in that area. But that is another hurdle. And the FDA, to its credit, is trying to make software as a medical device come up with a guidelines to how to make that quicker. And that first FDA approved screening for diabetic retinopathy took a long time. They had done all these studies, and then the FDA said, no, you have to do it in primary care. So now we have guidance. We don't have to go through that again. And they're really trying to make this much easier for approvals.
Mm-hmm. That's great. That's great. Thank you very much. Here's the next question. Have you had any experiences talking to people who are really skeptical about AI? Please tell us about those experiences, those conversations.
Yes, there's a lot of people who really don't believe it because they like to understand and they like to see what's going on. That's why I think the explainable AI and how to present it to the clinicians is critical. You need to gain their trust because AI will make errors, right? It's not 100%. You never get an ROC curve of 1.0. So another challenge is to present the data in a way that the clinician could assess whether that this is likely to be accurate or not. And I think those heat maps can help, because if the heat map is not showing an area that makes sense, that we know from the pathophysiology of glaucoma, we know that the patterns that we see in glaucoma, then perhaps for that particular patient, the clinician might feel that they can't rely on AI. However, in some of the examples that I showed where the patterns match, then the clinician, and if we present this to the clinician in an appropriate way, that they could have confidence that for this particular patient, the AI algorithm works, that would be great. Now, I hate to say this, but clinicians also sometimes are not 100% accurate as well. And these algorithms are very accurate, so that the likelihood of error at least is relatively low, but we really want to find out. And when we were doing these algorithms, we really look at the eyes and the OCTs and the photographs, et cetera, of the patients in which the algorithm failed, because we really want to learn from that. Sometimes it's very simple. It was a poor quality photograph or something like that, okay, well, a clinician would probably disregard that photograph because it's poor quality, but we have to teach the AI algorithm to do that as well. So sometimes when we're looking at these errors, it can help us make the AI algorithm better. So I think that I'm a skeptic by nature and by training, and only recently, because I see this evidence, and I think that more people like me who are skeptical will come around when they see that the algorithms are consistent, they're very accurate, but we have to use them appropriately and use them in an ethical. We need to preserve privacy, and there's all these different things that they have to be implemented appropriately. And that's also something that lots of people are working on in terms of implementing in an ethical, secure way that is appropriate for medical management of glaucoma and other diseases.
Mm-hmm. Thank you very much. Next question. Is AI available to be used in managing glaucoma treatment outside of the research today?
I don't think there's any commercial AI systems, at least approved in the United States. I know people are working on it. The same group that brought forth the diabetic retinopathy FDA approval has a glaucoma, in the pipeline, and other companies have glaucoma in the pipeline. But I don't think there's anything approved yet in the United States.
So I'm sure it will happen soon. And we have time for one more question, and it's kind of a piggybacking on what you said before, but I think it's an important one as well. What do you think excites and concerns physicians simultaneously about using AI in healthcare?
Well, I think one thing that clinicians might be concerned about replacing, right, the clinician. I don't think that's true. I think some subspecialties might have more of a concern than ophthalmology. I don't know, maybe radiology, where they're just looking at and don't have the same kind of patient interaction, at least some radiologists, I shouldn't say. But I think for ophthalmology, I think it'll free up time to spend more time talking about treatment options and for treating the clinicians. I think clinicians, change is hard. They've been practicing a certain way for a long time. And so it's challenging to, change your practice. But I think that the positive aspects of this outweigh the challenges and the disadvantages.
Well, thank you so much, Linda, for this fascinating talk and for your brilliant research. Of course, we are eager to see how it develops. I would like to thank everybody in the audience for joining us today and for your great questions. This webinar is recorded and could be reviewed again on our website under the Events tab. I hope you will continue joining in for our many webinars, and I hope you will continue supporting the important research of the Glaucoma Foundation. Thank you very much and have a great night. Bye-bye, everybody.